Hello guys, Spency here again. Today we're going to tackle the last of the reaction balances called the overall atomic balance. Now, unlike our previous two balances, this balance only requires basic material balance techniques from our first long exam. We also don't consider a generation term for this type of balance. So an atomic balance is the balance in which we balance the components without a generation term. These components are usually atomic elements like hydrogen instead of hydrochloric acid or carbon instead of carbon dioxide. So our balance now could be written as out is equal to in. The main challenge for atomic balance is finding out which parts to balance in. Additionally, our DOF thus becomes unknowns minus independent reaction species minus non-reactive species minus other constraints. Now, if you are unaware of the concept of independent species, please refer to our extent of reactions video. Now, let's consider the combustion of methane. If 100 moles of water comes out and 1000 moles of methane enters the reactor, how much comes out? First, we analyze which element is present in both. If you answered hydrogen, you are correct. Now we know that hydrogen is constant in both sides. We first consider the source of the inward hydrogen, which is only methane. Then we also consider the source of the outward hydrogen, which is the water and the unreacted methane. Thus, our reaction balance now looks like this. Now, using the power of shift solve, or if you want, you could use simple arithmetic, you will get the CH4 out as 950 moles. Easy peasy, unlike the two other reaction balances. Now, let's discuss the pros and cons of atomic balances. The one major pro is that the stoichiometry of this reaction is irrelevant. So you could have the unbalanced chemical reaction and yet you could still solve the system using atomic balance. Additionally, this balance only uses basic material balance techniques. However, this could give you several equations with several unknowns. So at one point in my life, I considered 5 equations and 5 unknowns more than what the calculator had the power to solve. So let's consider this chemical engineering problem. A reactor system was established so that the reactant stream at 40% moles of uric acid, 40% hydrochloric acid, and 20% potassium hydroxide at 1000 mole per hour will react through the equations. If the effluent stream contains 375 mole per hour sulfuric acid and 300 moles per hour hydrochloric acid, determine the complete combustion of the effluent stream and the percent conversion of potassium hydroxide, yields of potassium chloride and potassium sulfate, and the selectivity of potassium chloride over potassium sulfate. Now, we are supposed to solve this using atomic balance. So we are now going to go over to our calculation chamber and start solving this problem. Hello guys, welcome back to the calculation chamber, and today we are going to calculate the problem as mentioned before using overall atomic balance. Now, as good chemical engineering students, we should draw the diagram first. So let's draw the diagram. So I took a basis of 1R, and thus these are the results. 400 moles of this is HCl, then 400 moles of H2SO4, then we have 200 moles of KOH. Then going out of such, we have 300 moles of HCl and 375 moles of H2SO4. Now, to show to you that it is not required that you need the stoichiometric relationships of each of the substances, I'm just going to write the certain reactions. I'm just going to write the reactions as they are. So plus HCl. I'm not going to write any stoichiometric coefficient. H2O plus KCl 2KOH plus H2SO4. Oh, sorry, I wrote 1. I'm just going to cancel that. K2SO4 plus H2O. Now, first thing you need to do in an atomic balance is that you have to determine which are your atomic species. Your atomic species did not necessarily mean that they have to be atomic elements, but they have to be conserved throughout the reaction. So I have K, I have OH, it's preserved because I could write H2O as H2O could be equal to HOH. So I could write OH, I could write SO4, I could write Cl, I could write H, and yeah, that's technically it. So I could write 5 different balances. So first I'm going to start with the SO4 and Cl balances because they are very, very easy. So let me start with the SO4 balance. So that's 1 times 400 because you could find 1 mole of SO4 in H2SO4, then there are 400 moles of H2SO4, so we equate that to the 375 moles, multiply that by 1 since there's 375 moles here, then plus 1, where could we also find SO4 here in K2SO4. So NK2SO4, wherein NK2SO4 equates and K2SO4 equates to 25. I hope everything's clear now. Then we go with Cl, so that's again 1 times 400 because there's 1 in HCl here. Then since HCl is the only source for Cl here, we get the equal sign. Then we have 300 multiplied by 1 plus 1 multiplied by the KCl created. Thus, using shift solve, NKCl is equal to 100. Next, let's do the OH balance because it seems to be a lot easier. Oh, sorry, no. In the NOH balance, yeah, let's just do the NOH balance first. So in here, you have 1 times 200, which is equal to, you have 2 sources of your H2O, but you don't know you have 2 sources here. You have your KOH plus your NH2O. However, you don't know these two, so let's just move on to another balance. Let's use the K balance. So if we're going to use the K balance, that's 200 multiplied by 1 is equal to NKCl plus NK2SO4 plus NKOH. Because we have KOH lingering after in the product stream. After such, we could get a value for NKOH which is equal to 50. If we could get this, we could always also get the value of this, which is 150. Now, you could just use, I'm just going to do the H balance so that I could say that what I did was legitimate. So if I do an H balance, that's 1 times 400 plus 2 times 400 because I got it from HCl and H2SO4. You don't need to count the H here because it's part of the OH group. Equates to 150, which could be found here. So remember, H2O is HOH plus 300, which comes from the HCl here, plus the 375 multiplied by 2, which comes from the H2SO4. Thus, we could say that this is maintained because, yeah, this is equal to this. Now, we're just going to get the few stats again. So that's conversion equates to 200 minus 50. This is in minus out over in. You will get approximately 75%. Our selectivity, we get the amount of KCl, which is 100. Then we divide it by the other amount, which is K2SO4, which is 25. You get the selectivity of 4. Next, we calculate for the yield of KCl, which is approximately 100 divided by 200, because complete conversion of KOH to KCl here will yield to amount of 200, so that will be 50%. Same thing will happen for K2SO4, so that's 25 divided by 100, that would be 25%. So there you go. We solved the problem through atomic balance. This is proven much easier than extent of reaction and molecular species balance, because this is just basic ChE 101 first LE skills. So that was our video, guys. Thank you for watching. If you want to subscribe to our channel, you could do so with the logo above. And if you want to check out for more 101 videos, you could click on the video down below. Thank you for watching, guys, and good luck on your long exam.